Hi guys, in this video I'm going to talk about low pass filters. Actually, we are focusing on passive first order low pass filters. Okay, so let's dive into the topic. Low pass filters, and we are focusing on passive first order. First of all, I want to show you what is the magnitude frequency plot of a passive low pass filter. Okay, so this is the plot. This is omega, which is frequency. Actually, it is angular frequency. And y-axis is magnitude. The plot is like this. Here there is a special point omega c. Oh, actually here it is omega c. We can name it as cutoff frequency. There are some special facts that we can observe here. This graph is for an ideal filter. For an ideal filter. And we can observe there is an steep attenuation here. So here it is, steep attenuation, and we can see this filter is passing only low frequencies. Actually that is because this filter is called as low pass filters. Okay, and high frequencies are attenuated. That's why the magnitude is 0 according to this plot. Okay, so low frequencies are passed, high frequencies attenuated. Okay, that's it. Next, we are going to talk about the circuit arrangements that we can draw for passive low pass filter. Passive low pass first order filter. Okay, okay. So, circuits. Passive first order. Yes. Here's the first circuit that we can draw for passive low pass filter. This is the voltage source, and here is the resistor, and here is the capacitor. Here are the output terminals, plus, minus. Let's name the components. This is the capacitor and this is the resistor. The impedance is 1 over c omega, and this is just R. The output voltage is V out and input voltage is V in. This is the first circuit. This is the second circuit. Here is the voltage source, and here is the inductor, and here is the resistor. Output terminals are here, plus, minus. Let's name the component. Inductance is L, resistance is R. Inductance of the impedance of the inductor is L omega, and for resistor it is just R. Output terminal voltage is V out and input terminal voltage is V I. So, what is the next big question? Actually, it is why these circuits are called as low pass filters. Why? So let's write Y first. Y for this and Y for this. Okay. Let's uh, let's dive into that. First of all, let's check how circuit behave at low frequencies. At low frequencies, let's check about the impedance of the capacitor, which is C equals 1 over C omega. When omega is low, this whole term is high. It means the voltage across the capacitor, which is Vc, is also high. Okay, why is that? Because Vc proportional to the impedance of the capacitor. I think you get it right. So then at high frequencies, Cc equals 1 over C omega, and omega is high. When omega is high, this whole term is low. It means Vc is low. Actually, what is Vc here? It is the output voltage, because Vc equals V naught. Okay. So what this mentioning is, at low omega, the output voltage waveform is high, and at high omega, the output voltage waveform is low. Actually, more clearly, it is mentioning us that when the frequency associated with the input voltage waveform is high, the output voltage is attenuated. So the circuit is working as an ideal low pass filter. Okay, right. Then next we will go into the second circuit. As usual, at low frequencies, here it is CL, because the impedance is frequency dependent with respect to the when it comes to the inductor. Okay, so CL is L omega. We are concerning about low omega, and this whole term is low. It means VL is low, and it means Vc is VR. VR is high. When the voltage across the inductor is low, it means voltage of the resistor is high, because of the voltage dividing principle. Okay. Okay. Then at high frequencies, CL equals L omega, and we are concerning about high omega. When omega is high, this whole term is high. It means VL is high, and it means VR is low. So again, as the previous case, at low frequencies, VR, which is the output voltage, is high, and at high frequencies, VR, which is the output voltage, is low. It means When the omega, the frequency associated with the input voltage waveform is high, the output voltage waveform is attenuated, which means this circuit is working as an ideal low pass filter. I think you got it. Okay. Now we are going to analyze the circuit that we discussed previously. Okay. So let's divide the sheet into two. First of all, uh, and this is the first circuit. Here's the voltage source plus, minus, and the resistor, and here's the capacitor. These are the output terminals, plus, minus, and here is the resistor R and capacitor C, and impedance is R, and Laplace domain impedance is 1 over Cs. Here we are using the Laplace domain because it is very much easy to derive formulas in Laplace domain. Okay, I think you are familiar with Laplace domain. Yes. So the transfer function Hs is V out divided by V in. Here V out is V naught and V in is V in. This equals 1 over Cs divided by S plus, it is 1 over Cs plus R, and this gets simplified into 1 over 1 plus CRS, and it again gets, we can rearrange it as 1 over RC divided by 1 over RC plus S, and we can further rearrange this formula as omega C divided by omega C plus S, where omega C equals 1 over RC. Okay, then let's talk about the second circuit. This is the voltage source plus and minus, and here is the inductor, and here is the resistor. These are the output terminals, plus, minus, and we have inductor here L and resistor R. The Laplace domain impedance of the inductor is Ls, and for resistor it is just R. The output voltage is V naught, and here is the input voltage. So as previous, we can write the Laplace domain transfer function Hs equals V out divided by V in equals R divided by R plus Ls. We can rearrange this formula as R divided by L divided by R divided by L plus L, and we can kind of simplify this as previous, omega C divided by omega C plus S, where omega C equals R divided by L. Okay. Actually, I want to make you notice some important points here. The common format we derived ultimately is same for the both circuits. Okay, it is only the omega is varying here. Next, some important task we are going to do. we are going to do. Okay, so we are going to convert this Laplace domain transfer function into frequency domain. How is that is done? Actually, we substitute j omega into s. So next we can derive h of j omega just by substituting uh, s with j omega for both the circuits. Okay, so h of j omega equals, as usual, v out divided by v in omega c divided by omega c plus j omega. And by this we can obtain the modulus of h of j omega as omega c divided by square root of omega c squared plus omega squared. Okay, and also the phase angle of h of j omega, it is 0 minus tan inverse. Guys, I am referring to this when I am taking the phase angle. Okay, 0 minus tan inverse omega divided by omega c, which means minus tan inverse omega divided by omega c. Okay, so here these are the final results that we want. So let's do the same for the second circuit. H of j omega equals v out divided by v in, which is omega c divided by omega c plus j omega, and we can arrive at the modulus of the transfer function as modulus h of j omega equals omega c divided by square root of omega c square plus omega squared. And the phase angle of transfer function h of j omega is 0 minus tan inverse omega divided by omega c, which is minus tan inverse omega divided by omega c. So as before, these are the ultimate results that we want to plot the graph. Okay, yes guys, next we are going to plot the graph of sj omega and phase angle of hj omega. Okay, now we are going to talk about the plots. Actually, before that, I want to specify about the common formats that we find as ultimate result for both circuits. Okay, so let's write them. Common formats. Hs is omega c divided by s plus omega c, and magnitude of h of h of j omega is omega c divided by square root of omega squared plus omega c squared, and the phase angle is minus tan inverse omega divided by omega c. Okay, so next we are going to square this and divide the paper into two. So first of all, I want to talk about the magnitude plot associated with this magnitude plot. This is y-axis and this is x-axis. This is omega and here it is magnitude of the transfer function. Okay. So what will be the maximum value that h of j omega can hold? Actually it is 1. That is because h of j omega equals v out divided by v in, and v out is always less than or equal v in. So in ideal situation we can expect for low pass filter at low frequencies v naught equals v in, that is v output equals v input. Okay, so the maximum value will be 1. So here it is 1. Then when omega is increasing in this direction, what will happen? Omega is increasing, so h omega is also decreasing, h omega is decreasing. So the plot will be like this. Okay, and yet there is a special point, that is the cutoff frequency omega c, and that will happen when the value of h of j omega is equal to 1 over root 2. Okay, okay, that's it guys. Next we are going to talk about the phase angle, the phase angle of h of j omega, right? So first of all let's draw the axis. Here the y-axis and here the x-axis which is omega, and here the phase angle. Okay, okay. So when omega is 0, what will be the phase angle? Here we are interested about this omega. Okay, so when omega is 0, phase angle theta is also 0. So the graph is starting from this point. Okay, okay. Then when omega is increasing in this direction, what will happen? Actually when omega is going to infinity, the phase angle will be going to minus tan inverse infinity. It means minus 5 over 2. Okay, so the part will reach minus 5 over 2 and the plot will be like this.